to get the headphones. Hold on. I knew I was forgetting something. I need the headphones to do my sound check. Well, I mean, I don't need them, but might be better to use the headphones so that we don't get some sort of echo effect when I play the sound. Let me plug that in real quick. And let me check on this screen if everything sounds fine. And it does. And is everything visible? Can I see my hand moving there? Yes, I can. All right, then we are good to go. Headphones have been put away. Let's see what we want to do for today. So, as I mentioned at the end of the previous stream a couple hours ago, I was thinking we could do either more rotational dynamics or energy for today, and I think I'm pretty much settled on doing energy. Since I've already got some review videos for force and rotational dynamics, but not so much for energy. I guess with energy it seems simple enough that I rarely feel the need to review it. I feel like students grasp energy pretty well, unless they haven't been given a very good foundation in it to begin with. Then students might struggle a little bit. So let's go ahead and look at just some classic problems. Well, maybe not all classic problems, but let's look at a couple of typical problems and maybe a few atypical ones and see what we can do with them. So I'm just going to use my usual book for this, and if you're wondering what my usual book is, here you go. It's College Physics by Surway and Fawn. It doesn't really matter which edition you use. It's the same book with a couple of questions shuffled around here and there. Anyway, what do I want to do first? So I think the biggest issues for people that struggle with energy is understanding the concept of total work, how to calculate the work from, I mean, the process itself is fine, but recognizing when you actually have to follow that process tends to trip students up. And then the other big thing relating to that is after you calculate your total kinetic energy, or sometimes before, relating it to, wait, did I say kinetic energy or work? After calculating your total work, or sometimes before, relating that to the kinetic energy. That's something that a lot of students tend to forget. So let me take a look at a problem that really helps emphasize the connection between work and kinetic energy. Actually, before I do that, let's just prove the work kinetic energy theorem. So the work kinetic energy theorem, also known as the work energy theorem for short, because adding the word kinetic in there is a mouthful, too many syllables. Work kinetic energy theorem. And I have new markers at the ready. I actually should probably get those out right now. Let me figure out which markers were the ones that were dying last time. Yeah, this one's as good as dead, so that one's on the chopping block. Was this one dead too? Looks like it'll die today, but it's still kicking for now. And then, was yellow okay? Yellow seems perfectly fine, much to my dismay. Okay, so it's the pink one for now, and then the, I guess, burgundy is what we would call it, is coming up soon. That one's going to the trash, and let's see, what are we going to replace it with? I mean, those are just two shades of purple there. Might as well pick one of them now. And yeah, we'll go with this. I guess we'll call that lavender. It's the lighter of the two purple shades. Anyway, work kinetic energy theorem. So basically, what it states is that the total work, or the net work done on an object, whether you prefer the term total or net is up to you, but as long as you understand the concept, it doesn't really matter what you name it. Total work is equal to the change in kinetic energy of an object. Total work done on an object equals the change in that object's kinetic energy. So proving this is not too bad. The total work can be calculated in two ways. You can either take each force acting on the object and take its dot product with the displacement. I'll call it delta x, but it could be a delta y or some other displacement that's neither horizontal nor vertical. F1 delta x plus F2 delta x plus F3 delta x. The delta x should be the same for all of them, because delta x is just the displacement of the object under the influence of each force. I guess you could have different delta x's if different forces acted for different parts of the displacement of the object. So like if you applied 3 different forces on an object and one of them you only applied it for half of the displacement, while the other 2 acted on the object throughout its entire displacement, I guess then we'd be justified in treating each of these displacements separately, but usually the displacement is going to be the same, usually. But there you go. So total work is just, you calculate the work due to each force individually and you add them up. Or alternatively, if all of the forces are acting on the object over the same displacement, you could simply take the sum of those forces. You could factor out the displacement and you could take the sum of those forces and take the dot product of that with the displacement of the object, and you should get the same total that way as well. Okay, well, if it is the case that it's net force times displacement, then we know what net force is. Net force is mass times acceleration, so work total equals mass times the acceleration of the object dot the displacement of the object, and acceleration dot displacement, the dot product is just going to give us the magnitudes of each of these multiplied by each other and also multiplied by the cosine of the angle between them. Let's assume, for example, that we have an object that's just being pushed in a straight line, just pushed horizontally. Let's say we have an object, there's some net force on it that causes it to move by that much. And let's assume that force is constant the whole time, and let's just take the horizontal component of the net force on this thing. If we dot it with the displacement, then your angle is just going to be 0 degrees between the direction of the net force and the direction of the displacement. So that's cosine of 0, which is 1. So your dot product reduces or simplifies to a regular product of magnitudes. So this just becomes m times a delta x. Okay, well, if I use my equations of kinematics, I can replace a times delta x with another quantity. If you remember your equations of kinematics, especially the third one, we know that v final squared equals v initial squared plus 2 times the acceleration times the displacement. And of course, some of you might have teachers that just call this v squared while calling this v0 squared, or some of you call it v2 squared equals v1 squared plus 2a delta x, whatever you prefer. And some people even write the delta x as a d, which I don't really like, but it is what it is. What I don't like about d is that it's easily mistaken for distance rather than displacement. And those two concepts are quite different from each other if you know your physics. So that's why I prefer the delta x. But anyway, subtract v initial squared on both sides, and you get v final squared minus v initial squared equals 2a delta x. Divide by the 2, which is the same as multiplying all this by 1/2. And there we go, we have a delta x now. So work total equals ma delta x equals m times 1/2 v final squared minus v initial squared. And if I distribute the m and the 1/2, I get 1/2 m v final squared minus 1/2 m v initial squared. 1/2 mv final squared, that's the final kinetic energy. And 1/2 mv initial squared is the initial kinetic energy. So if we're doing final kinetic energy minus initial kinetic energy, there you go, that's your change in kinetic energy by definition. So there you go, that's the work kinetic energy theorem. Total work done on an object is equal to the change in that object's kinetic energy. Very, very important for situations where you don't know the forces acting on an object, but you do know what its speed was before and after the work was done on it. And if you know your mass, along with those two pieces of information, you can calculate the total work that was done on the object. So let's see if I can find a problem in here that actually requires us to use that. I'm trying to find something that would actually force you to use kinetic energy to calculate work. So far I'm seeing things that give you other options. Oh well, maybe we'll run into one later. Let's just pick something for now so that we're not sitting around here looking for the golden problem. Okay, how about this one, which says a mechanic pushes a 2.50 times 10 to the 3 kilogram car, so 2,500 kilograms. That is not a very good looking car, but let's pretend that thing is a car. And this thing is 2,500 kilograms. And it's pushed from rest to a speed of v. It's pushed from rest to speed v. And it says that that is done by doing 5,000 joules of work. Work done, 5,000 joules. And then they say during this time the car moves 25 meters, neglecting friction between car and road. Find V and the horizontal force exerted on the car. Find V and find, I guess we'll call it force applied, the horizontal force applied to the car. Let me draw what that force applied looks like. It's going to look something like this. And they said that the car moves 25 meters. So I'm going to call that delta x equals 25 meters in magnitude. All right, so the first part, finding v, is actually quite easy and doesn't require knowledge of the displacement at all. You do have a way around using the work-energy theorem, which is you could just use this displacement to calculate the force, and you could then use the force and the mass of the car to calculate the acceleration, and from there you could just use regular kinematics to find v. So that is definitely an option, but it's not the best option because it involves more steps and takes more time. It's much faster to use the work-energy theorem if the total work is 5,000 joules. Oh, I think this marker might be on the chopping block, actually. Not quite yet, but I can feel it. Like the stroke is a bit... there's a lot of resistance when I push on it, and that's how I can tell it's starting to run low on ink. Anyway, 5,000 joules for the total work is equal to the change in kinetic energy is equal to 1/2 times the mass of 2,500 times v final squared, which is our unknown v, minus 1/2 the mass times v initial squared. Initially it was at rest, so times 0 squared. And there you go. Very quickly we can do, well, I can multiply the 2 over to there, and that'll give me 10,000. And then 10,000 over 2,500, 100, well, I can cancel 100 on both sides, and yeah, 2 times 50 is 100, and 100 over 25 gives me 4 is equal to v squared. So v is equal to 2. In this case, we'd say, I guess, positive 2 if we define right to be the positive direction. That's just what common sense would suggest. Sometimes you can figure out the direction of v. Other times you won't be able to without some additional information provided in the problem. Oh, and I guess I can see the shadow of my document camera on the page there. I don't know if that was always there or if this is happening because I've changed my setup a little bit. I did get myself a new desk, which is a lot wider and gives me some more space, but also required me to move some things around. So I guess now I'm at an angle where the light hits my my document camera from a more, I guess, direct angle. Well, that shouldn't be too much of an issue. But I'll keep an eye on the screen just in case this little patch of darkness makes something unreadable. And maybe next time I'll figure out a solution to this little problem. Maybe I can rearrange my desk setup a little bit. Or maybe change my lighting. Well, I mean, apart from using another lamp, because this is a ceiling lamp that I'm using right now and I can't really move it, so we'll see. If I can figure something out for next week, then great. Otherwise, we'll just have to deal with it. Anyway, back to the problem. So we got v equals 2 meters per second, and we did it the easiest way possible. If you tried to do this the other way by using the work and the displacement to calculate the force, and using that with the mass to calculate acceleration, and then using kinematics equations, I think you can tell just from that description alone how many steps it would take just to reach this same result that we were able to get in essentially just 2 steps, maybe 3 if you wanted to do every algebraic step individually and write it out instead of doing a little bit of mental math to save time. But there we go. That's the first part. The second part is calculate the horizontal force exerted on the car. We could have done this right from the get-go, but just as I described a minute ago, we can get that force by just using the work equation. Work is equal to force times displacement times the angle between their directions. If our force is applied horizontally to the right and our displacement is horizontally to the right, then cosine of theta is cosine of 0 degrees, which is equal to 1. And we have our force applied is going to be 5,000 over a displacement of 25. 5,000 divided by 25 meters. 50 over 25 is 2, so 100 over 25 is 200. Force applied equals 200 newtons, which sounds rather small. You would think that a car would require something on the order of thousands of newtons to move it, but that's only if you're trying to lift it. If you're trying to push it horizontally, assuming that there is no friction that you're working against, pushing it horizontally is actually quite easy. All right, so that was that problem. Can we look at another one that at least recommends the work energy theorem, if nothing else? Well, I mean, the problem itself wouldn't recommend it, but what I mean is, can we find another problem where work energy theorem is the recommended approach? Okay, we can do this one. So it says a 70 kilogram base runner. A 70 kilogram base runner. I guess I'll write that data here. A 70 kilogram base runner begins his slide into second base, so we're talking about baseball here, when he is moving at a speed of 4 meters per second. So V initial equals 4 meters per second. Coefficient of friction between his clothes and earth is 0.7. Coefficient of friction is 0.7. They said 0.70, but I'm not too worried about sig figs. Leave that for chemistry. He slides so that his speed is 0 just as he reaches the base. So V final is going to be 0. And part A says how much mechanical energy is lost due to friction acting on the runner. What is the mechanical energy lost? That's our first question. And then the second question is how far does he slide? We'll call that delta x. Okay, well, for change in mechanical energy, he's not going to be moving relative to the Earth. He's not going to be moving vertically, so we don't have to worry about any change in potential energy. That means our change in mechanical energy is really just the change in kinetic energy. If change in mechanical energy is change in potential energy plus change in kinetic energy, and there's nothing about this problem that indicates that anything is going to change in terms of potential energy, then really what we're looking for is the change in kinetic energy. And the change in kinetic energy is the total work done. Which we will need for the second part. But for the first part, to figure out how much mechanical energy is lost, all we have to do is compare the initial to the final kinetic energy, which is pretty easy to do. Change in kinetic energy equals kinetic energy final minus kinetic energy initial equals 1/2 70 times final speed is 0 squared minus 1/2 70 kilograms times initial speed was 4 squared. Okay, that's all 0. And here we've got 4 squared is 16. 16 over 2 is 8. 8 times 70 should be 560. So negative 560 joules. Kinetic energy was lost. They started with a higher speed than what they ended with. They lost energy. Okay, so that takes care of the first part. Second part, what is the displacement? And come to think of it, do we even need the coefficient of friction here? No, we don't. No, we don't. Unless we're being asked to calculate the force, which we're not, then we're fine. We don't even need that friction coefficient. Interesting. I guess that would give you another avenue for solving the problem in case you forgot that change in kinetic energy is equal to total work, but we can just, oh, wait a minute. What am I saying? No, we do need that because To calculate the displacement, we need to know the force. Okay, never mind. I'm just having a brain malfunction tonight. Okay, so change in kinetic energy equals total work, so negative 560 equals the total work on this person. Well, let's see which forces are acting on this person as they slide. They have their weight pulling them down, so we've got mg. There's a normal force acting up on them. And there is a friction force acting opposite to the direction they're moving, and they're moving in this direction. So that is, I probably should have used a different color for it so that we don't mistake it for one of our forces, but that's your displacement. Normal force and gravitational force are going to do zero work because they make a 90-degree angle with the displacement. So 0 from normal force plus 0 from gravitational force plus the work from the friction force equals the total work. So 0 plus 0 plus work friction. So your negative 560 equals the work of friction is going to be the force of friction times the displacement times cosine of the angle between them. The angle between them, the displacement is going to be opposite in direction to the friction force. So that's a 180-degree angle. Cosine of 180 degrees is -1, so that's a negative there. And we can go ahead and cancel these negatives out. So 560 equals the magnitude of the friction force times the displacement, while friction force is coefficient of friction times normal force. We know the coefficient of friction is 0.7. What is the normal force? Well, we know this person doesn't accelerate vertically just through common sense. We know they don't accelerate up or down, so their acceleration in the vertical direction is 0. And if acceleration in the vertical direction is 0, then net force in the vertical direction is also 0. So I guess I'll say over here, net force y equals 0 equals forces up, normal force, minus forces down, mg. Therefore, if you add mg to both sides, you get normal force is equal to mg in magnitude. So we can go ahead and substitute in mg over there. So 560 equals mu mg delta x, and if we plug in those numbers, 0.7 times 70 times 9.8, or 10 if you prefer. The AP exam does allow you to substitute 10 for g. Sometimes the problem straight up tells you to use 10 for g. And delta x. Okay, calculator time. So 560 equals 0.7 times 70 times 9.8. That's 480.2. 560 equals 480.2 times delta x divided by 480.2 on both sides. 560 divided by 480.2. And I'm getting about 1.166. I'll say 1.17 for my displacement. So let me switch colors back to burgundy. I guess I'll write it over here. Delta x equals 1.17 meters. And there we go. So those are our two answers. Well, actually, it said how much mechanical energy is lost due to friction. So actually, this isn't the right answer. The right answer is just 560 without the negative sign, because it's asking how much, not what's the change in kinetic energy. If it was asking what's the change in mechanical energy, then negative 560 would be correct. But if it's asking how much, then it's asking for the absolute value. It's already assuming that the energy is lost. They don't need the negative sign there. They're asking how much is lost. What's the magnitude or size of the loss? Very important distinction there. Usually that's more of a concern for the chemistry students. Very many times the chemistry students will be asked, especially in the thermochemistry topics, they'll be asked how much heat is absorbed or released versus what is the enthalpy change of a reaction, and you have to be careful with the wording so that you don't use signs where they're not needed. Alright, so that takes care of that one. Is there anything else in here that I would like to go over before I take a look at conservation of mechanical energy with multiple objects? Okay, how about this one? It says an outfielder throws a 0.15 kilogram baseball at a speed of 40 meters per second and an initial angle of 30 degrees. What is the kinetic energy of the ball at the highest point of its motion? This one is actually really simple, as long as you don't overthink it. A lot of students forget with the motion of a projectile that at the highest point the velocity is not zero. It has a vertical component of zero, but it also has a horizontal component that's unaffected by gravity. The only way to change the horizontal component of velocity for a projectile is to have some sort of horizontal force act on it, and gravity does not act horizontally. You would need something like air resistance or rocket propulsion or something like that. So, object thrown at a 30-degree angle. When it's at the peak, it's still moving horizontally, if not vertically. So they said the mass was 0.15 kilograms. And it was initially thrown at 40 meters per second. And that's it. What's the kinetic energy at the highest point? What is the kinetic energy at the apex? Well, for that, we just need to know the speed at the apex. So we can do, let's see, if I just do the cosine component of this, that should be equal to the horizontal velocity up here. The horizontal velocity is constant after all, so if I just get the horizontal velocity at the beginning, I should be good to go. So 40 cosine of 30 degrees is about 34.64. Is about 34.64 meters per second. So then we would have kinetic energy at the apex is equal to 1/2, the mass is 0.15, times, let's see, 34.64 squared. And that's giving me 89.99. I'm just going to go ahead and round it to 90 joules. Actually, let me see real quick. If I did 40 cosine 30 times 40 cosine 30, that's exactly 1200, and then 1200 times 1/2 times 0.15, yeah, is exactly 90. So in fact, 90 is correct. The 89.99 business is just due to rounding errors, which is why it's good not to do your rounding until the very end. I definitely encourage you to try and work through a problem by doing as much as you can algebraically to isolate the one thing that you're solving for before plugging it all in at the end. A lot of times you'll get things canceling out that reduces the amount of work you have to do, and also it just gives you practice for doing those expression problems that they like to do on the AP exam, where they ask you to solve for an expression for the kinetic energy or the force or whatever it is in the problem in terms of a bunch of constants and variables that they give you. And it's also good for situations like this where rounding errors can throw off an otherwise very clean answer. Okay. Oh, right. I wanted to ask another question. How much work is done on this baseball by gravity? So that's my bonus question. What is the work done by gravity on this thing? Well, if you throw a baseball in the air and if you assume no air resistance, what forces are acting on the baseball? Let's say I have my baseball here at some point in time. What forces are acting on it? Nothing except for gravity. The force of gravity is the only force acting on it, and the only force acting on it must be the only force doing work. So the work done by gravity is actually just straight up the total work done on this object. And what is total work equal to again? That's right, it's equal to the change in kinetic energy. So to get the work done by gravity, all I have to do is get kinetic energy final minus kinetic energy initial. Well, kinetic energy final at the top we just calculated as 90 joules. So work done by gravity equals kinetic energy final is 90 joules minus kinetic energy initial, 1/2 Mass is 0.15. And I see this marker is on its last legs. And then V squared is going to be 40 squared. V initial squared is 40 squared. And if I go ahead and do that math, 1/2 times 0.15 times 40 squared is 120. 90 minus 120 is negative 30. Negative 30 joules. The work done by gravity is negative 30 joules. If I asked how much energy is lost against gravity, then you would just say 30 joules without the negative sign. There was one other thing I wanted to comment on here, which was the kinetic energy when your velocity is two-dimensional is not the sum of the kinetic energies of the horizontal and vertical components. Be very, very careful about that. That is incorrect. You wouldn't do, let's see, what would the vertical component of this be? So 40 sine of 30 would be, well, sine of 30 is 1/2, so that would be 20 meters per second. You can't do, if I did 1/2 the mass times 20 squared, what would that give me? 1/2 times 0.15 times 20 squared is 30. And if I did 1/2 the mass times 34.64 squared, well, we did that before, that's 90. And the initial kinetic energy is not, wait a minute. Actually, in this case, I think it might be, right? Because we said this was 120. Oh. Well, that's not supposed to happen, but I guess this is just a special case. Interesting. Wait. Actually, does it work? Hold on. I might be wrong here. So, does 1/2 mv squared equal 1/2 mvx squared plus 1/2 mvy squared? Well, because we can do, I can cancel out the 1/2 everywhere and the m's, and that would leave us with v squared equals vx squared plus vy squared, which is true. Huh. Okay, it actually does work. Wait a minute, then what am I thinking about? What if I did, so if I go ahead and calculate, this was 120. If I do 120, let's say 120 cosine of 30, does that equal the kinetic energy of the horizontal component? Does that equal 90 joules? It better not. I mean, I can already see that it's not, but let me see what the calculator gives us. 103.92. Yeah, that's definitely not the case. 103.92 0.92 most definitely does not equal 90. Okay, so yeah, this is rather interesting. I feel like I should have known this a long time ago. You can get the kinetic energy associated with a two-dimensional velocity by simply adding the kinetic energy associated with each of its components, but you cannot take the total kinetic energy of a two-dimensional you can't take the total kinetic energy of an object moving in 2 dimensions or higher and then decompose that. Why is that? Well, hold on. I think I have a bit of a mathematical insight. It just came to me. Because if we calculate the kinetic energy from each component separately, then what I would be doing is 1/2 m and then v sine theta squared plus, or actually no, the x component is cosine, but that's okay. We don't have to. Addition is commutative, so we can add the vy squared first. 1/2 m vy squared plus 1/2 m vx squared. Vx squared is v cosine theta squared. And if you factor out the 1/2 m and the v, then you're left with sine squared plus cosine squared. And we know sine squared plus cosine squared reduces to 1 if you remember your Pythagorean trig identity. And I forgot the square there. And yeah, okay, so I can see why this works now, and I can also see why this doesn't work. The reason this doesn't work is because your 120 would be 1/2 mv squared, and then you're multiplying it by cosine of 30 only once. If you want it to work, you would have to multiply it by cosine squared of 30 to get the kinetic energy associated with the horizontal component of the kinetic energy. I never knew that before. You learn something new even after teaching physics for over 10 years. Yeah, if I do 120 times cosine squared of 30, so times cosine 30 times cosine 30, we get 90, like we're supposed to. Okay. I learned something new today. So I guess you can decompose kinetic energy into quote-unquote components. I say quote-unquote because kinetic energy is a scalar. It's not supposed to have components, but I think you get what I mean by components here. You can divide kinetic energy into components by taking the squares of the trig functions of the angle made with the horizontal or the vertical. Probably not something you should be eager to use. I would still recommend just getting the total velocity, the total two-dimensional velocity all packaged into one thing, and then squaring that and multiplying it by half the mass to get kinetic energy that way, instead of trying to do it component-wise, because the chances of screwing this up are very high. And besides, doing things from first principles will get you the result, and you're not going to be taking that much of a shortcut learning this new thing. I mean, I've gotten by without it for over a decade now, you can too. So yeah, I would not put too much stock into learning this, but yeah, that's an unexpected surprise right there. I feel like I should have known that a long time ago. But hey, maybe that's why I stay in business. Because I do these problems over and over again so many times that I eventually discover these little things that other people don't discover because they put physics behind them as soon as they're done with their class. Okay, moving on. Which problem would I like to do next? So next up, I would like to do this problem with the multiple blocks is a classic that I like to show students. I'm assuming here that you already have experience with using conservation of mechanical energy, so we have ourselves a table and we've got some pulleys. And we have a number of blocks over here, 3 to be exact, and they are labeled M1, M2, and M3. Let's see, it says 3 objects with masses M1 equals 5 kilograms, M2 equals 10 kilograms, and M3 equals 15 kilograms, respectively, are attached by strings over frictionless pulleys as indicated in the figure. The horizontal surface is frictionless, and the system is released from rest. Using energy concepts, find the speed of M3 after it moves down a distance of 4 meters. So I guess we'll call it delta y, object 3, is equal to, I'll call it negative 3 meters. Okay, so the reason I like to show this problem to students is because it helps you understand the idea behind conservation of energy for a system versus conservation of energy for an object. The condition for conservation of energy is that the non-conservative work has to be 0. What is non-conservative work? Any work done by forces that are not conservative. And rather than memorize which forces are not conservative, it's easier to remember which forces are. The conservative forces are the gems. The conservative forces are the gems: gravity, electric, magnetic, and the spring force, sometimes called the elastic force as well. And the spring force is only for springs that obey Hooke's law, so ideal springs. If you have weird springs that don't exert force proportional to how much they're stretched or compressed, then it's not going to work. It's only for springs where the force increases linearly with stretching or compression. Anyway, so what forces are acting on these objects? We've got the force of gravity acts on each of them. So that's m3g, m2g, and m1g. Not drawing my vectors to scale, by the way. We've got tension forces, so I'll call this force of tension 1. That should also experience a force of Ft1 as well. Whoops, did I accidentally write a 2? Ft1. And on this side, it'll experience force of tension 2. And this thing will also experience force of tension 2. Technically, the force on this side of the rope and this side of the rope are going to be slightly different, but we are assuming that these pulleys are light and frictionless, so don't worry about the rotational dynamics going on here with the pulleys. We can worry about that when we do rotational dynamics problems. Here you can assume that the difference between this tension force and this tension force is negligibly small. Anyway, one last force, which is the normal force. So the easy way to discover that non-conservative work is 0 is if there are not any non-conservative forces. Unfortunately, that's not the case here. Tension is not a conservative force, and normal force is not a conservative force. Okay, the next best thing is if there are non-conservative forces, the next best thing is to show that they do no work. Well, the normal force doesn't do any work because this object is going to move horizontally and the normal force is vertical. Cosine of 90 degrees between those two directions gives you 0. So non-conservative work done by normal force, 0. Good news so far. What about the tension force? The tension force is not conservative and it does do work. This object, I guess it's going to move to the right since block 3 moves down. So as this thing moves to the right, force of tension 1 is going to do some sort of negative work. Since it points opposite to the direction of the displacement, force of tension 2 is going to do positive work on block 2. So we've got some non-zero work due to tension here. The mechanical energy for block 2 is not conserved. What about for block 1? Well, there's going to be some displacement upward, and the force of tension 1 is also pointing upward, so that's going to be positive work. Definitely not 0 done on block 1. And force of tension 2 points up while the displacement is down, so force of tension 2 is going to do negative work on block 3. So all 3 of these blocks have some sort of non-conservative work being done on them. Is it game over? Can we not use conservation of energy anymore? Well, if you treat the objects individually, no, the energy is not conserved, but what if we treat them as a system? What if we treat them as a group? So let me go ahead and write in the displacements for each of these. So this one is going to have a displacement of, I guess I'll call it delta y1 equals, wait, did I copy the number wrong? I did. This is supposed to be 4 meters. Glad I caught that. The problem said 4 meters. And this is going to be positive 4 meters then. And this thing, I guess we'll call it delta x2 is equal to positive 4 meters. I'm going to assume right is the positive direction for this thing. Not that it really matters, because when calculating work we use the magnitude of the displacement anyway, and we let the angle between displacement and force determine our signs for us. So let's go ahead and see what the work is on the system. What is the non-conservative work on the system as a whole? Non-conservative work on the system as a whole is the non-conservative work on object 1 plus the non-conservative work on object 2 plus the non-conservative work on object 3. Let's calculate each of those. So non-conservative work on object 1 is force of tension 1, whatever it is, times 4 times cosine of 0, because up and up there's 0 degrees between those directions. So we have work non-conservative for object 1 is force of tension 1 times 4 times cosine of 0. Okay, what about non-conservative work on object 2? So we've got force of tension 1 times 4 times cosine of 180, because force of tension 1 is to the left while the displacement is to the right. That's 180 degrees between those directions. Cosine of 180, that's going to be equal to -1. Plus, we've got another non-conservative force doing work here, force of tension 2. Force of tension 2 times 4 times, this time force of tension 2 is to the right, displacement is to the right, that's cosine of 0, which is again 1. I know a lot of students like to skip on writing out the cosines, and that's fine if you really have mastered this and you know what you're doing, but accuracy before speed. If you tend to make mistakes forgetting to consider the angle when calculating work, I would get in the habit of doing this even if it is redundant, because redundancy is a great way to improve your accuracy. Redundancy is a good way to avoid fatal mistakes. There is a reason why 18-wheelers have 18 wheels. It's not because they need all 18 of those wheels. It's just because with that many wheels, you can afford to have 1 or 2 wheels go bad and still keep rolling and drive those goods to their destination before having to take the truck to a repair shop or something. Same idea here. Accuracy and reliability via redundancy. Something that a lot of CEOs could stand to learn. If I had a nickel for every time a CEO made a bad decision because they thought redundancy was inefficiency, quote unquote. Anyway, work non-conservative on object 3 remains to be calculated, so that's going to be force of tension 2 times the magnitude of the displacement is 4 meters again, and the directions are up versus down. That's a 180 degree angle between those two directions, cosine of 180 degrees. That's going to give us a -1. And now we have it. Now we can add our non-conservative works, and let's see what we get. We get 4 force of tension 1 plus negative 4 force of tension 1. So those cancel out. And then we've got 4 force of tension 2 plus negative 4 force of tension 2. So the work done by the tension forces cancels out when you treat the 3 blocks as a system. Of course, this is something that a lot of students automatically assume when they see this problem, but assuming it and getting the correct answer doesn't mean that you actually understood the underlying concepts, which is why I really like to go over this problem. Getting the right answer for the wrong reasons is not as good as you might think it is. Sure, you're getting the points and you're getting the grade that you like for it, but are you actually learning? Anyway, what did I want to do next? Well, I guess we can say that this sum is equal to 0. Don't have to rewrite it again. So when you add the non-conservative work for each of these objects, that turns out to be 0, which means then that the change in mechanical energy for object 1 plus change in mechanical energy for object 2 plus change in mechanical energy for object 3 equals 0. You could also rewrite this as, oh boy, here we go, big equation. Mechanical energy final for each object equals mechanical energy initial for each object. So I guess potential energy initial for object 1. Actually, hold on. I'm going to call it potential energy 1 initial rather than initial 1. Let me restart. And this marker's dead. All right, time to get its replacement, which is... which color do I want here? I mean, we just got rid of a pink, but here we go. A brighter pink. So, where were we? Potential energy 1 initial plus kinetic energy of object 1 initial plus potential energy of object 2 initial plus kinetic energy of object 2 initial plus potential energy of object 3 initial plus kinetic energy of object 3 initial equals all of that again, but final this time. So potential energy 1 final plus kinetic energy 1 final plus PE2 initial plus KE, or wait, final, I should say, plus KE2 final plus PE3 final plus KE3 final. And I guess this is another thing that I should have commented on earlier, but I know a lot of people like to use capital U for potential energy, which is fine, and capital K or even a capital E for kinetic energy, which is also fine, whatever works for you, as long as you as long as you understand whatever as long as you understand whatever notation you're looking at. You can learn from anybody's example. Well, I shouldn't say no two physicists use the same notation, because it's very common for, well, how do I word this? There's usually like there's usually about 2 to 4 different ways, 2 to 4 different conventions for naming variables that physicists tend to adopt. And, once you see enough of that, you start getting used to it. You start getting used to the fact that different people use different labels for their variables, and as long as you understand the meaning of what you're looking at, you're going to be fine. So I wouldn't get too hung up on which Greek letter or whatever to use for each variable, or even which style of notation to use for your subscripts. As long as you write down something that makes sense, you'll be fine. Anyway, let me go ahead and get rid of the things that will be 0. So I guess first I need to define my 0 line for potential energy, and I can do that separately for each object. I don't have to use the same 0 line for all objects. I can give each object its own 0 reference line for potential energy. For object 2 in particular, it's not going to experience any change in height, so potential energy initial for object 2 is going to be equal to potential energy final for object 2. So these are going to cancel out. They're going to cancel out because they're going to be equal to each other. What else? Initially, the system is at rest, so all of the initial kinetic energies are zeros. And that leaves us with the potential energies of object 1 and object 3. For object 1, I'm going to say that the 0 of potential energy is over here. I'm going to say that's where my potential energy of object 1 is 0. And for object 3, I'm going to say down here is where the potential energy is 0 for object 3. So that's where potential energy 3 is 0. I could have very well done it up here, and then that would have made this whole left-hand side 0, which is an approach you can take, and honestly, I feel like I would have preferred it, but I don't know. I think for the sake of providing an example that's not too simple, I decided I didn't want the whole left-hand side to be 0, so this is what I'm going with for this instance of solving this problem. Okay, so we've defined it to be 0 for object 1, so yeah, that just leaves us with PE3 initial is going to be, well, it's going to be 4 mg more than it is at the final position, and come to think of it, at the final position, that's going to be 0 since that's how I've defined it to be. Okay. Then let's go ahead and move on to a new sheet of paper, and let me switch colors as well. Which color should I go to now? Let's go for green. I wanted to switch to burgundy, but I feel it's too close to this new pink color. Okay, so we've got potential energy 3 initial. So I guess I'm going to call that mg, or I should say m3g time. Let me write it again. m3g times its initial height from the 0 line I've defined for it is 4 meters. So it's positive 4 meters above where I've defined 0 to be, equals let's see, potential energy 1 final. So that's going to be 4 meters above the 0 line I've defined for it. So that's going to be m1g times positive 4 meters higher than the 0 line I've defined for it. And then plus a whole bunch of kinetic energies. So plus 1/2 m1 v1 final squared. I'll just call it v1 squared because v initial was 0 for all of them. Actually, I'll call it v final squared. All 3 of these objects are going to be moving at the same final speed, so I can just give them all one name and I don't even need to number them. Plus 1/2 m2 times that same v final squared plus 1/2 m3 times that same v final squared. Okay, and v final is what we're trying to solve for. If I factor out the v final squared, then I'm left with v final squared times, in parentheses, I'd have 1/2 and the sum of m1, m2, and m3. So let me go ahead and actually write that out to see what it looks like, instead of forcing you to picture it all in your head. And I'm also going to subtract m1g times 4 on both sides, might as well. So we have, I can factor out the 1/2 and the v final squared, and I'm left with m1 plus m2 plus m3. m1 plus m2 plus m3. Okay, and I can multiply by 2 and divide by that sum, and I will have my final expression. So, and take the square root. Hold on, that's not the color I wanted. This one. Multiply by 2 and divide by that sum, so 2 m3g times 4 minus m1g times 4 and then divided by m1 plus m2 plus m3. Equals v final squared, and if I want v final I can just take the square root. I'll just take the positive root because we only want magnitude here. For direction, I guess it depends on which block we're talking about. For block 3, direction is down. For block 2, direction is right. For block 1, direction is up. But the magnitude is the same for all 3 of them. So yeah, this is what I was talking about earlier. I could have plugged in numbers as early as over here. But if you hold off on plugging in your numbers, then you can get some sort of expression like this. I guess I did plug in the 4s at the very least, but still, being able to do all this algebra before plugging in any numbers is definitely something worth practicing. It just helps you with doing those expression problems that I talked about earlier. And these problems will usually also ask you to do some sort of analysis. They'll ask you to, do follow-up questions like, what happens to the final speed if the first mass increases, or the second one increases or decreases, or whatever? What happens if only the second mass increases versus if the third mass, I don't know, doubles, for example, and then you have to take into consideration the fact that the third mass contributes to the numerator. They might ask you something like, what if m3 increases by 2 while m1 decreases by 2. So the denominator is still the same, but now your numerator has changed. They might ask you questions like that, which are easy to analyze if you can put together an expression like this, which they will usually ask you to do anyway before they ask you those analysis questions. But now I'm rambling. Let's go ahead and plug in our numbers and see what we're supposed to get here, and see if we can squeeze in a couple more interesting problems before we have to wrap things up for tonight. So square root of fraction 2 times parentheses m3 was 15 kilograms, right? Oh, I didn't write them down here, but according to the book, m3 is 15, m2 is 10, and m1 is 5. So 15 times 9.8 times 4 minus 5 times 9.8 times 4. I could have just done 10 times 9.8 times 4, but lack of insight on my part. And then for the denominator, we've got 5 plus 10 plus 15. Let me see, did I copy all those numbers incorrectly? 5 times 9.8 times 4, and 15 times 9.8 times 4. All of that looks good to me. Did I remember to close those parentheses? Yes, I did. Then we are good to go. I'm getting about 5.11. 5.11 meters per second, and this marker is dead. See, I was expecting this ever since last week. Which color should I take now? I don't want to take the darker purple. Let me dig around here for something else. How about... I'm not being given that many options, huh? I mean, I already have pink, so the red isn't really the best of ideas. I guess gray? I hope it'll look significantly different from navy blue. Let's try it out. Oh yeah, that's noticeably different from this one. Okay, yeah, it works. Okay, gray is now available to us. I need to look around. I'm pretty sure I have another box of these lying around somewhere. If not, then I'm going to have to do some shopping, but not right away because I still have about, how many of these do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I still have 11 of these left, and they'll definitely last for a couple months at the very least. So I've got time to buy new ones if I need them, but I'm pretty sure I have another pack of these lying around somewhere. Anyway, what did I want to do next? Look for another problem. All right, here we go. We could do elastic potential energy, but I feel like we'd end up reviewing that anyway when and if I do a simple harmonic motion review. there's that problem that I like to give to my students a lot of the time, but... Oh, actually, I think I know the perfect problem. Let me see if I can find it in here. Oh, found it. It was directly above the problem we just did. And here I was looking at some of the pages further ahead. Okay, so for this problem, we are told Tarzan swings on a 30-meter long vine, initially inclined at an angle of 37 degrees with the vertical. What is his speed at the bottom of the swing if he starts from rest versus if he pushes off with a speed of 4 meters per second? So questions are V final, if V initial equals 0, and V final if V initial equals 4. Those are the two questions we are being asked. So, 30-meter long vine. I'll draw it down here for the extra space. So this thing is 30 meters long, and it's initially held at 37 degrees with the vertical. And that's all the information they give us. What is his velocity at the bottom of the swing? What is his velocity down here? His V final, or V bottom, if that's what you prefer to call it. So this one tends to give students trouble because there's some geometry involved. There is some conservation of mechanical energy to apply here. So if Tarzan starts off over here, let's say that's him standing over there. He's going to swing down and he's going to experience a change in height. His change in height is going to be the size of that gap right there. That's going to be his change in height. And a lot of students have trouble figuring out how we're supposed to get that change in height. Once you can get it, you can just use conservation of energy. You can get the change in his potential energy, and from there get the change in his kinetic energy. So the real difficulty with this problem is not from the physics aspect of it, it's from the geometry. As a lot of the electromagnetism students would know, geometry is super important in physics. Okay, so how do we do this? Well, first thing I would want you to see is that this vine is basically the radius of a circle. I'm probably not drawing it perfectly. Yeah, it's kind of lopsided, but there's your circle right there. And so every distance from, I guess we'll call it the node that the vine is attached to, every point on this circle is the same distance from that node. So this distance over here must also be 30 meters. This distance over here must also be 30 meters. But there's another shape we can see in here besides a circle. Other than a circle, there's also a right triangle in here. And that right triangle has that length over there as one of its sides. We've got this right here making up one side of our right triangle, and then this side here making up the other side of it. And there's the 90-degree angle for your right triangle. We can figure out what this distance is. If we know this is 30 meters, if we know the hypotenuse of our right triangle is 30 meters, and we know that angle is 37 degrees, then all we have to do to get the adjacent side length is multiply 30 by the cosine of 37. So this is 30 cosine of 37 degrees. And from there, we know that if this yellow distance is 30 meters, and if this green distance is 30 cosine of 37, then subtracting the two will give us this pink distance, delta h, that we are looking for. So delta h is equal to 30 minus 30 cosine of 37. And you can factor out the 30 if you want to be fancy about it, and write it as 30 times 1 minus cosine 37 if you like. But once you've got that figured out, the rest of the problem isn't too bad. So I guess I'll switch to this lavender color. I want to do, first of all, I need to check if my mechanical energy is conserved. A lot of times students will jump to just assuming that it's conserved. Don't do that. We need to check what is the non-conservative work equal to. So we're not going to consider the normal force acting on Tarzan when he's standing before he lifts off, because we're only looking at what happens during the swinging, and the swinging happens after Tarzan loses contact with wherever he's standing. So the normal force we don't have to take into consideration. Once he starts swinging, the only forces acting on him will be the force of tension, which is going to be parallel to the vine, and the force of gravity, which is straight down. Okay, force of gravity is conservative, so the non-conservative work done by it is, by definition, 0. Gravity cannot do non-conservative work. Any work done by gravity is conservative. I don't want to say by definition. Well, it is by the definition of a conservative force, not by the definition of the gravitational force specifically. But now I'm arguing semantics. Let's just move on. So gravity we don't need to worry about. Tension, however, is a non-conservative force. We do need to show that the work done by it is 0 before we can claim that mechanical energy is conserved. Okay, so force of tension acts parallel to the rope, and when you're swinging on a rope or a vine, you're going to be moving tangent to the arc of the circle traced out by that vine or rope as you swing along it. So this circle I've drawn, at every point you are going to be moving tangent to that circle. So at the beginning, Tarzan is going to be moving, which color should I use? I'll use green here. So at the beginning, the direction of Tarzan's displacement is going to be there. Then at some point, say down here, the direction of his displacement is going to be that way, while the direction of the tension force on him is going to be that way. And when he's at the very bottom, the direction of his displacement for a split second is going to be straight to the right, while the tension force on him is going to be straight up. So you can see, if you keep on drawing these at other points along this circular arc, you see that the direction of his displacement at any moment in time is going to be perpendicular to the direction of the tension force acting on him. And if the force and displacement are in directions perpendicular to each other, well then, work done by tension equals force of tension times, I'll call the displacement delta S, times cosine of 90 degrees. Cosine of 90 gives us a 0. So there we go. Our non-conservative work is 0 because the one and only non-conservative force we have here does no work due to being at a 90-degree angle to the displacement at all times. Okay. Now that we've proven that, we can say that the change in mechanical energy is 0. Or that the change in potential energy plus change in kinetic energy is 0. And what is the change in potential energy going to be? Let's see. Switch colors. Let's do navy blue. So 0 equals the change in potential energy is mg times the change in height. Mg times the change in height. You could have also done, we could have also done mgh final plus 1/2 mv final squared equals mgh initial plus 1/2 mv initial squared. We could have done this, and then you'd subtract mgh final on both sides, and if you group those together, you'd have mg factored out times h initial minus h final in parentheses, which would still be that delta h. So that's why I'm doing it this way, just to skip a couple of algebra steps. But you're more than welcome to do it this way, and it'll work fine. You could define one of these heights to be 0. I guess maybe you would define the lower one to be 0. But anyway, plus change in kinetic energy, I'll just leave that as delta KE for now. Actually, no, why am I leaving it? I need to substitute it in, but I need more space. So let's copy this over to here. 0 equals mg times 30 minus 30 cosine 37 plus change in kinetic energy equals 1/2 m times v final squared minus v initial squared. We can divide everything by m. 0 divided by m is still 0. That m cancels out. That m cancels out. So we don't even need to know Tarzan's mass, which is good because it wasn't given to us in this problem. And the only remaining unknown to plug in is v initial. So in one case we want to plug in 0, in the other case we want to plug in 4 and solve for v final. So let me rearrange this for v final. How would I go about doing that? So subtract all that over to the left-hand side. Wait a minute, did I define my delta H correctly? No, I didn't, because my delta H is supposed to be negative. Yeah, my delta H is supposed to be negative. It's supposed to be, because it's initial height minus, wait a minute. Yeah, if I'm defining down to be the negative direction, then delta H is supposed to be negative over here. Okay, I missed a negative sign that I should have included from the outset. So if we add that over to the left-hand side of the equation now, we'll be left with, well, I might as well plug in the numbers. You know what? No, I'm not going to plug them in just yet. Let's continue on another sheet. So if I add that stuff over to the left-hand side, then I'm going to get G times 30 minus 30 cosine 37 equals 1/2 V final squared minus V initial squared, multiply by 2 on both sides, so we get 2G 30 minus 30 cosine 37 equals V final squared minus V initial squared. Add V initial squared to both sides, and there's our expression for V final squared, and then you can square root both sides of this to get V final's magnitude. And plug in V initial equals 0 versus V initial equals 4, and you've got your two answers. Note that when V initial equals 4, V final is not going to be simply 4 more than what it is when V initial is 0, and we'll see that once we actually plug in the numbers and calculate. So with V initial equal to 0, I would do square root of 2G, so 19.6, times, in parentheses, 30 minus 30 cosine 37 plus 0 squared. Square root of that gives me 10.88. So V final equals 10.88 meters per second when V initial equals 0. And then if I go back and copy paste that thing in my calculator and replace the 0 with a 4, I get 11.59. V final equals 11.59 meters per second when V initial equals 4 meters per second. So yeah, don't trust your intuition too much. I think that's the ultimate lesson that a physics course is supposed to teach you, if you can follow with the math. Always question your intuition. Sometimes your intuition is right, but other times your intuition is wrong, so don't rely on your intuition too much. And if you feel that your intuition is right, try and prove it. But over here, intuition would suggest a much bigger difference than what we are getting. We're getting a difference of, maybe some of you would have realized early on that This number was not going to be 4 more than this number. And some of you may have thought that maybe it'll be square root of 4 more, but that's not the case either. As you can see, the difference between 10.88 and 11.59 is less than 1, in fact. It's what, 0.59 plus another 0.12 is 0.71? Yeah, 0.71. Barely over 2/3 for adding 4 meters per second in over here. So I guess it would depend on how much length the vine has. The longer the vine is, the less significant a change in initial velocity will be in terms of what your final velocity turns out to be. Let's see. I'm trying to think through like how it would feel physically swinging on a long vine versus a shorter one. Is there anything like from, I guess, physical intuition there that can be related to what we've learned here? I mean, there's gotta be something, but I'm not the best brainstormer. I'd have to sit on it and think about it for a while. Because on a shorter vine, kicking off with a higher speed is definitely going to have a bigger impact on what your final velocity is. Well, I guess you could argue that with a shorter vine, this 30 minus 30 cosine 37 is going to be so much smaller that your final speed at the bottom of the swing is going to be really close to your initial speed because there's barely going to be any height change. In fact, if the vine is short enough, you might not even experience a height change at all. Not because your height isn't changing, but because your perception of your changing height, you wouldn't perceive yourself having that much of a change in height. Yeah, we're not human meter sticks. We aren't really good at detecting really small changes in position. I feel like there's something even more significant that I could say here, but it's just not coming to me. I feel like there's some sort of like real life observation we could connect to this that would make it even more intuitive than that, but that's the best example I've got for now. Let's see if we can squeeze in one more problem. Is there anything here that would be good to include that doesn't take too much time? Because we're kind of short on that. That's just another swinging position or swinging problem. We don't need to do that. We just did the Tarzan one. That one's just a friction problem. We kind of did that already with the baseball player sliding to second base. Yeah, I don't know. I'm not really seeing anything that good that we could do here. I think we can just call it a day here then. Well, actually, here's one quick one that we can do. Work done by a variable force. Work done by a variable force. So when your force is constant, or when you know the average force over a given change in position, you can just calculate work by doing force times displacement times the cosine of the angle. A lot of times that cosine is just going to be 1. Cosine of, whoops, I didn't mean to say 0, cosine of theta. But what if your force is variable? If you know your calculus, this is no problem, but if you don't know calculus, there are still some specific cases you can do. So here's a problem that says the force acting on a particle varies as in the graph shown. Find the work done by the force as the particle moves from position 0 to position 8 meters, and then from 8 meters to 10, and then from 0 to 10. So they've got a graph that looks like this. They've got the x component of some force, or a force that's just completely in the x direction. Either interpretation is fine here. And then they've got x, the position, and they've got, let's see, 2, 4, 6 for newtons of force, and that's force in newtons, and position in meters. And for position, they've got 2, 4, 6, 8, 10. Oh, and I'm going to want to mark -2 on here. And it looks like we don't really need it, but they've also marked -4 on the graph. Okay, and if we draw the graph, then the graph looks something like this. It peaks at 4, and it also has a sharp point at, let's see, that is between those two values. And that is at time 10. And then it turns back up. So something like, hold on, where does it hit 0? It hits 0 at 8. Okay, probably should have gotten out a ruler so that that would come out straighter, but it's good enough for our purposes. All right, there you go. So you've got a variable force versus position graph. If you don't know your calculus, then you can calculate the work done by a varying force off of its graph by simply calculating area under the curve. Why would area under the curve equal work on this graph? Well, let me draw another graph and show you what it looks like for a constant force. For a constant force, the force would just be some fixed value, and the graph would just be perfectly horizontal. So this is whatever that force is. And then if you calculate the change in x between these two positions, then you've got your delta x. And delta x times whatever the force is also equal to the width times height of this rectangle. So it does make sense that multiplying the units on the vertical axis, the force units, by the units on the horizontal axis, the displacement units, would give you area in energy units, joules. So by that same logic, we can use area under the curve here to figure out what work is done by a force. And also note that since work can be negative, I shouldn't even call it area under the curve. I should call it area between the curve and the horizontal axis. So this area over here would amount to positive work. This area over here, however, would amount to negative work, and I don't want to color over the 10. So that's another thing to keep in mind. If your shaded area is below the horizontal axis, that should be expressed as a negative quantity, unless there's some sort of physical reason for you to take the absolute value of it, which is a possibility in some cases, so keep an open mind there. Anyway, they said calculate the work done for x equals 0 to x equals 8. So from here to here, well, that's just the area of that first triangle. And then they said calculate it from 8 to 10. So that's from this point to this point. So half of the second triangle, not all of it. And then they said calculate it from 0 to 10, which is basically just combining those first two triangles they asked you to calculate. Okay, we can do that. So we've got area of the first triangle, 1/2 base times height. Height is 6 newtons. And base is from 0 to 8 is 8 meters. So area is equal to 1/2 8 times 6, 4 times 6, which is 24 joules. I guess I should call that work. Okay, so that's work from 0 to 8. I'll call it work 1. Work 2, they want it from 8 to 10, so they want that is going to be 2 meters, and then for the height, that's going to be -2 newtons, the negative indicating that it's in the negative x direction. And oh, actually no, hold on, because that actually reaches between -2 and -4. I should say -3 newtons. Almost missed that. And yeah, once again, it's equal to, I guess I'll call it area 2 equals 1/2 base is 2 meters times height is -3 meters. In geometry, we can't have negative heights, but in physics we can, because it's not actually height that we're measuring here, it's force. So 1/2 times 2 times -3 is just going to be -3 joules. And then they say, what's the work from 0 to 8? That's just going to be work 1 plus work 2. Equals 24 minus 3 is 21 joules. All right, and that's work done by a variable force, and I think with that, we can conclude for tonight. Hopefully this has been helpful, especially to those of you that are in need of review for energy. I might be able to dig around here and find some more that we could do next week, or perhaps next week we could do momentum and collisions, or circular motion, or a mix of the two. I don't even know yet. Actually, for circular motion, something that's been coming up a lot, I've been seeing people ask about, is questions that involve density. So I might want to actually dedicate some time to that. So yeah, we'll see. So next week will probably be momentum or circular motion. If I don't do circular motion next week, then it'll probably be the week after that. But I definitely want to make sure to cover those density type problems. They aren't related to circular motion directly, they're more related to gravitation, which is usually taught in the circular motion chapter, so that's why I'm saying circular motion, but really it's circular motion and gravitation. But yeah, if I find any other good problems with energy, I know we didn't really talk about power, but power isn't really talked about that much in mechanics anyway. It's usually more important in electromagnetism when you're trying to calculate the power dissipated in different devices within a circuit. But yeah, if I come across any other problems that I think are really important to cover here, then we might do some more energy next week. But that's enough of me rambling. Take care. I'll see you guys next week, and look forward to whatever next week's topic happens to be. Or, if you don't approve of any of the topics I suggested, make sure to show up so you can ask your own questions instead. Anyway, that'll be it for me. See you next week.